In this video, I will give more motivations for the fact that on Rn up to a scalar multiplication, there is only one locally finite Borel measure that is translation invariant. Such measure, we know it's the Lebesgue measure. To prove this, we will adopt a viewpoint that is very general, and it only requires that our space is a topological group that is locally compact. Let's give the formal definition of a topological group, and then on it we will consider the invariant measures that are the one called Haar measures. Okay, let's start with the definition of topological group. So a topological group is a topological space let's call it G, that is also equipped, so it's equipped with a topology, but also is equipped with a group structure and this group structure should be compatible with the topology, means for which the so if you have a group structure, we have the multiplication law and the inverse map. So we require the multiplication map. So the map goes from G times G into G, that to any pair X and Y associate the product given by this multiplication, and also the inverse map goes from G to G to every X associate minus X. So these two maps are continuous with respect to the topology of G, and also observe that in the case here G times G, we're considering the product topology, right? So here G times G is seen with the product topology. Okay, good. So this is the abstract definition that we are going to use, but let's see some examples. So the simple example is, of course, is our favorite group, that is Rn. So x, y goes to, now we write the multiplication as a sum, and the inverse is minus x. What did I write here? Of course, here I got it wrong. It's not minus x. Here I should write x minus 1. So yeah, x goes to x minus 1. This is the inverse map. Notice that I did a mistake here. I corrected. So now instead, when it's abelian, we call it minus x. So these maps, of course, are continuous. Okay, now more generally, if we have a norm vector space, and of course, whenever we have a norm, we equip the vector space with the topology induced by the norm. So I claim that this is a topological space. Of course, like we write exactly in the same way the operations, and now let's prove it just what one should check. We should check that. Okay, let's check the sum. So so I take this map. So now I take a pair x, y, and then I take increments in x and increments in y, and I take the difference. So I take x plus u, and I sum y plus v, and then I see how different is this from x plus y. And I should say that this goes to 0 when x and v, when u and v goes to 0. Okay, this is equal to u plus v, which is less than norm of u plus norm of v, and this quantity goes to 0 as norm of u and norm of v goes to 0. So the sum is continuous. Now, what about the inverse? So we have to take minus x plus v, and then we have to remove minus x. Okay, this is equal to minus u, sorry, v, which has the same norm of v, and of course this goes to 0 when v goes to 0. Okay, so this is the proof that also the inverse map is continuous on every normed vector space. Okay, so the previous two examples or what I'm saying, just vector spaces are commutative groups. So the group law satisfies x times y equal y times x, right? And whenever we have such a property, we write with the plus. Okay, next I want to take some non-commutative example. Next is a non-commutative example. Okay, example 3. It's called the general linear group. Okay, we fix some natural number. We denote with mat n to be the set of all n times n matrices with coefficients in R. So the usual matrices. And then we let GLN, also written as GLNR, to emphasize that we're taking real coefficients, all those matrices for which the determinant is different than 0. So let me also clarify that, therefore, a matrix is in GLN if and only if A is a n times n invertible matrix. Okay. Now we want to see this set GLN as a topological group. So we have to clarify the topology and clarify the group operation. Okay. Now let's first understand that the set of matrices is a topological group. or is a topological space first. So we see mat n with the topology via the identification of mat n with the coefficients, and we have n square coefficient. So this is every A in mat n has n square coefficients. However, also observe that the space of matrices is a vector space. Okay, is a finite dimensional vector space. Right? So this means that all the possible norms that we put in this space, they induce the same topology. But this is, again, this is a useful identification, okay, to give the topology. Okay, some remarks, maybe exercise for you. Okay, every element A, n by n matrix, so can be seen as a linear map A that goes from Rn to Rn, that to any vector in Rn associate the vector A times n in Rn, where we are seeing x, as a column vector, and we're seeing this, and this product is the matrix product, line times columns. And therefore, what we have that mat n is isomorphic to the linear maps from Rn to Rn. Now, on the linear maps from Rn to Rn, right? So these two are normed vector space. Fix, for example, the Euclidean norm, so this becomes norm vector space, and the linear maps form a norm vector space with the operator norm. So on this space, we consider the operator norm. Okay, so once we fix a norm on each Rn. So the fact to understand what's happening is that this space, now with the topology that we define as with the coefficient, is homeomorphic to the space of linear maps from Rn to Rn with the operator norm. The second remark is that the function determinant from the space of matrices into R is a continuous map. And this is because it can be calculated with some polynomial map of the coefficients. So therefore, the space GLN which is exactly the space that the pre-image is the set of, sorry, is where the determinant is different than 0. This, so it's a pre-image of an open set, R minus 0. This is an open subset of the space of matrices. Okay. So now it's clear what is the topology. Is the topology induced by the space of matrices, and it's an open set. Okay, now let's consider the operation. So the map from mat n times mat n into mat n, that to every pair AB associate A times B, this is continuous. Okay, it's continuous because it's going to be, again, it's polynomial in the coefficient. Each coefficient is a polynomial in the coefficients of A and B. And let me stress that what is the meaning of A times B? Okay, we can see it as composition of matrices or composition of maps. So multiplication of matrices or compositions of maps. So here, A times B can be seen as multiplication of matrices as well as composition of maps, of linear maps. Okay, and therefore the restriction of this map on GLN, it's a continuous map. Now let's go to the inverse. So the map that to every A associate the inverse matrix, let's pay attention because not all matrices are invertible. So this map, okay, let me see where A inverse denotes is the inverse matrix. This map is not defined if A is not invertible. And when is not invertible? It's exactly if the determinant of A is equal to 0. But however, on GLN, which is exactly where the determinant is different than 0, such a map is defined and is smooth. Why? Because from linear algebra, we have formulas to calculate the coefficient of the inverse matrix, and this coefficient is all in terms of okay, you have to divide by the determinant of the matrix, and then each coefficient is the determinant of some minor. Now it means it's a ratio of two polynomials, and the one at the bottom, that is the determinant of A, does not vanish, and therefore in the locus where the determinant does not vanish, the function is smooth. Okay, so conclusion of all this discussion: GLN equipped with multiplication of matrices and topology of matrices is a topological group. Good. The plan of this video is to arrive at a proof of the existence and uniqueness of invariant measures. So the plan is to show in a very general setting, that topological groups have unique invariant measures. Now, the general setting will not be all topological groups. There's still some assumption, very weak. And actually, the only thing we need is that as a topological space, this is locally compact, which is more or less saying it's finite dimensional. Uniqueness is always up to the multiplication of a scalar, up to a multiplicative factor. And invariant, we should pay attention because now we have two ways of translating a set, right? Either we multiply on the right or on the left, and this is different. It might be different because the space is not commutative. So we'll go back to this point, what it means. But the example should be clear. The example we want to think of and generalize is what's happening on our n. On our n, there exists a measure maybe let me say that this will be a consequence. We will see this. Okay, so as a consequence, we shall obtain that something that we already know, that on our n there exists a measure, a non-zero Borel measure, let's call it mu, that is finite on compact sets, and for which if we take a Borel set and we take a vector in Rn, the measure of the translation of this vector, of the set by that vector, is the same of the measure of the set. Okay, moreover, we have some uniqueness. Every two such measures differ by the multiplication or by a positive scalar. And of course, the Lebesgue measure is one such a measure. Okay, very good. So this is what we want to get to. So let's clarify now what is the new way of thinking of A plus V. So now this plus is we have our group on multiplication. So now let's define the translations. So, and now we will need to distinguish between left translations and right translations. Okay, so let's given a group G and fixed an element G in G. We have two maps. Okay, we have the one called LG. L stays for left, from G to G, to any H associate GH. You see, I put G on the left of H. So this is called left translation. By G. And the other map is RG. R stays for right. To every H, you associate HG. And this map is called right translation by G. Okay. Remember, the map that sends GH into G times H, this is continuous by definition of being in a topological group. So now if we fix G and we see it as a map only in H, then this mapping is continuous in particular. So as a remark, on a now topological group, left and right translations are continuous. So therefore, let me repeat that on a topological group, that is not commutative, it is necessary to distinguish between left invariant measures and right invariant measures. So let's give the definitions. Okay, so first definition, let's define right invariant and left invariant. So let G be a topological group then we say that a Borel measure mu on G is left invariant, if so the measure of G times A is equal to the measure of A is for all A Borel set of G and for every G element of G. Okay, so here before we had plus, now we just have a product where G is on the left. Equivalently, we can also write this we can write as if we have the push forward measure of G of mu, this is the same measure mu. Pay attention that when you push forward, you have to take the inverse map, but now it's the same of taking, if this is true for G, then it's true also for taking inverse, because every element is an inverse of its inverse. Okay, now similarly, mu is right invariant if mu is equal to the right translation push forward mu for all G in G. Okay. So now, as in the case of Rn, we don't want to consider all possible Borel, all possible measures. In Rn, we are considering the one that are finite on compact sets. Right? So now we have to restrict to the same type of measures on topological groups. So I will introduce a notation. So let X, or some terminology, be a topological space. And we said that a Borel measure mu on X is called Radon measure. Radon measure if it is, okay, one, is finite on compact sets, two, is outer regular on Borel sets, and three, is inner regular but just on open sets. Okay, this is the requirement that we want for a Borel measure. But let's remember, eventually we are going to restrict to locally compact groups, and when you have a locally compact group, you can very well think that the group is equipped with the topology comes with a metric, and the metric has balls that are compact. Okay, this is true only locally, because but you can change the distance to make it really in such a way that all balls are compact. So let me recall also this fact that if X is boundedly compact, is a bounded compact metric space, then every Borel measure that is finite on compact sets is regular. Okay. So you can very well think that radon measures are just Borel measures that are finite on compact sets. Let's continue with the definition. So a topological group is locally compact if, so okay, the first condition is to have not a pathological space, and this is actually some people or some author already include this in the definition of topological space. But okay, we require that points or singleton points are closed sets. And equivalently, one can say that equivalently, one where one is the identity element is closed. Two, and this is the very important assumption, that every point has a compact neighborhood. So every point is contained in the interior of a compact neighborhood. Okay, so for the last definition, so let G be a locally compact group, topological compact topological group, a left Haar measure, respectively right Haar measure, is on G G is a left invariant, respectively right invariant radon measure. Okay, on G. Okay, what we will prove next, and probably in the next video, is one, every locally compact topological group possess a left invariant or a left, just called it left Haar measure, left Haar measure. And two, if mu and nu are left invariant or left Haar measures on the same locally compact topological group, then there exists a constant, positive constant, such that one of them is a multiple of the other. We are going to prove these two theorems one at a time, these two parts one at a time.